Welcome to the last day, the afternoon of SDC. I know a lot of you are probably, pretty burned out by now, but hopefully this talk will be a little less of a brain strain than most of them that are going on today. My name is Bill Lynn. I'm a fellow at AMD. My background is storage. I've been in the storage industry probably better than 40 years now. I don't know if many of you attended the talk that Anthony Constantine gave on form factors, where he went out and talked about in the 50s there was the 24-inch drive and then the 20-inch, 14, And I looked at that list and I said, geez, I've worked on every one of these form factors except 24-inch. My first engineering project was a 14-inch removable pack design that held 10.4 megabytes, and it fit in a 19-inch rack and weighed 75 pounds. So it has been quite the ride from the storage point of view over the last 40 years. So what I want to talk about today is sort of demystifying how data flows through typical large language model training. The reason I did this is Pratik in the audience? No. So many of you, I don't know, have attended talks given by Pratik. He is probably one of the smartest people I have ever run across. He is a PhD. He's in our research group. And every time I talk to him and ask him a question, I have to go away for 3 or 4 days and think about what he told me because it just makes my brain hurt. He talks just in incredible detail and concepts that I have a hard time wrapping my mind around. So he did a large language 101 presentation last year, and I only understood about a third of it. So I decided, let's try and put something together that people can understand a little better. So as an introduction, I think most people have seen this slide many times. Essentially, when you're doing LLM training, you're taking in data from a huge array of sources and everything, and you bring this into a data ingest phase where you clean the data, you prep the data, you have to remove biases, you have to dedupe it, you have to make sure that the data makes sense. Now, there was a statement that was made earlier in the conference that I thought was really interesting is, you can make a large language model say anything you want it to say given the data you feed it. So large language models, these AI things, are not smart. They're not intelligent. They will tell you or feed back to you information that you feed to it. So the data that gets fed into these things is really important. There are a couple of examples like I remember seeing in the news that a lawyer used an AI engine to generate some example use cases that he wanted to present in court to support a case that he was working on. Well, he asked the AI model to give him 5 cases that supported this premise or this thought, and it spit out 5 cases. So he went and submitted those in court as supporting evidence, and 3 of them were valid. Unfortunately, the other 2 came from TV shows. So the judge was not really happy with that. So, you got to be really, really careful about, the data you feed it. You also have to be really careful about how you train it, in that a lot of these LLMs get trained to produce an answer. A great example of this is when they were first doing training LLMs to understand handwritten letters. So, they created this data set that was 27 by 27 pixels, and it had thousands and thousands of handwritten letters and numbers, and they said, they labeled those images as 3A, B, whatever, and they read it through this, fed it through this LLM. Well, the LLM got pretty much like a 99.6% accuracy at predicting these, whatever you fed it as a handwritten letter, it could accurately tell you what it was. The interesting part of it is if you fed it white noise, it would say it was a 5. It was absolutely certain that a random pixel grouping was a number or a letter because it never was fed the information that said this is not a letter or this is not a number. So it would take wild things and with absolute confidence say that this is something it's not. So you have to be really, really careful with these things. So I just wanted to illustrate here that you got to be careful with the data. You have to clean it. You have to dedupe it. You have to make sure it's accurate. There's a whole lot of efforts being done to remove biases from data sets. And so I'm not going to concentrate on those two phases, the data ingest or the data prep, but I want to talk about how the data flows through the actual training model, through the LLM. So this is a picture of Meta's Llama 3. And this came from Pratik's presentation. And this was, I looked at it and I was like, oh my God, what's going on here? It's like, it made my mind hurt. And I kept asking Pratik to explain it, and he'd just point at it and say, isn't it obvious? And I'm like, no. So this is sort of where I want to try and take this and make it a little more understandable as to what is going on here. So I want to go back to AI fundamentals. So a lot of these AI models are based on neural networks, and everybody talks about neural networks, and it's like, ooh, these are really cool things, And there are lots of different ways you can put the neural networks together. But essentially they consist of an input layer where you feed it tokens, they have some number of hidden layers, and then they have an output layer. And what happens is when you take data into these things, one of the things you have to do is you have to tokenize that data. You have to turn it into something the large language model can understand. So when you're dealing with language models like this, everything depends on context. So think of this. This is a really stupid example, but let's say you take a sentence like, bear bears, bear bears. So you've got one word, bear, but it actually has 3 different meanings depending on the context or where it is in that position. It can be either a noun, a bear, an animal. It can be an adjective where it says doesn't have clothing. Or it can be a verb where, to bear something or to, So large language models thrive on context. That's the only way they work. They have to understand the context of what's going in and what's coming out. So when you tokenize something going in, what you're doing is you're creating a vector. And essentially that vector is just a stream of numbers. And they can be 16K in length or 16K in what the AI guys call dimensions. So you have this very high dimensional vector, and all of those dimensions are used to create or carry weights that provide the context for what that token is being used for. So as the token flows through the inner layers and flows from node to node, those weights that are in that vector get modified to sort of enrich the context of how that particular token is being used. Because, like I said, you can feed it words, but words often have different meanings depending on the context that they're being used for. So as this thing flows through this, you can think of these nodes as essentially memory locations in a GPU's memory space. So what happens is each node has a bunch of different values that are associated with that vector, or with a particular part of that vector, I should say. And the lines that connect the nodes are essentially actions that the GPU compute units are using to transform those weights as it flows through the neural networks. So I didn't want to spend a whole lot of time on linear algebra because I hate linear algebra, but linear algebra is actually cool in the fact that it's the thing that makes using GPUs possible. Because linear algebra is essentially just a bunch of matrix multiplications. And GPUs are really, really good at matrix multiplication. If you look at essentially what happens in a node, as you're flowing that vector through, it takes each of those pieces of that, each dimension of that vector, and a node contains all the weights that it applies to those pieces or those elements of the vector, and it essentially does a weighted sum. It takes all of the elements of a vector, it multiplies it by all the different weights that are associated with that node, and it sums it together to give a value that gets passed to the next layer. And these layers, you know, I think, what is it? ChatGPT-4 has like 120 some odd layers in it. So you're doing just an incredible amount of compute in this thing. And the other thing I wanted to sort of emphasize in this is, as you feed tokens into this thing, for every byte of a token that you feed it, or every byte of data that you feed it, once you tokenize it, once you create these vectors, you're multiplying that data by, thousands and thousands of times. So the amount of ephemeral data that gets generated and moved through these GPUs is thousands of times more than the data that you're actually feeding it from the beginning. So you feed it a small amount of data, it blows it up into these giant vectors, it does all this math on these things as it goes through, and it pops an answer out the other end. So when you look at this, it's like, okay, this is really cool, and to make this really effective, you want to do this all in memory because you're doing these little tiny math operations. They're not giant operations in themselves. You're multiplying, like floating point 16 values together to generate an answer and blah, 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 all this stuff. So what you want to do is you really want to keep this thing in the GPU memory so that it has the fastest access to all of this data. And please bear with me, this will start making a lot more sense as I get a little further on. So, you can think of sort of the weights as the number of parameters in a model. You've got some of the big ones are like at 405 billion parameters. They're talking about 1 trillion parameter. So now you have all of this data that you really want to keep in memory. So the best way to, as you scale these things up and try to speed them up is, you really want to be able to split these things between multiple GPUs. You can't, you don't have enough memory in a GPU. GPUs, have a lot of HBM, but, they're on the order of, a half a terabyte or, a couple of hundred gigabytes of HBM. in a GPU. So what you want to do is, you want to split these models up between GPUs, but you really want to keep them in a single memory domain so that it's easy for the GPUs to reach out and grab weights and values from the different nodes as they're spread through these multiple GPUs. And this allows you to do a lot more processing in parallel because, as I said, this is just really a bunch of matrix math. It's a lot of matrix multiplications and everything. And the beauty of matrix multiplications is you can split them in a bunch of different ways and hand them off to different processors and let them crunch and then bring it all together in the end. So it's really easy to parallelize, and easy is in quotes. The guys that write the code for me will say, you're nuts, it's not easy, it's black magic and all that. But from a math point of view, it's pretty straightforward to split these things up and recombine them at the end. So the thing that happens here is when you split out of a single memory domain, you now have to, you split your problem, you assign one part of the matrix multiplication to one group of GPUs, another part to another group of GPUs. You go through and do this. At the end, you have to recombine the results. And this is sort of this mixing and matching of gradients. And everybody has to, all the GPUs have to come to a certain point. They complete their part of the operation, and then everybody has to synchronize. If you're in a single memory domain, that's really straightforward, easy. Actually, if you're in a single memory domain, you don't have to synchronize because everybody has access to everything else. But if you've split the problem between multiple memory domains, then you do have to do this gradient sync between the different domains and then resynchronize, essentially. So this is sort of, there we go. This is sort of a very simple data flow. You do a forward pass, you compute error, you do a backward pass, you do an all reduce to synchronize everything, and then you go back, update your model, and then you feed it another batch of data and go through this thing over and over and over again. So one of the things in training that kind of stumped me for a while, and I was trying to figure out how this thing really understands, is if you think of inferencing's pretty much just the forward pass on this thing. You feed it a token, it goes through a forward pass, it pops out an answer. Training is a little bit different in that you feed the model, the model starts out at pretty much a random state. It has just some random assigned weights to it, to all those 16,000 dimensions within a vector. And you feed it a chunk of data, it goes through, it pops out an answer. So what happens is, in training, you're training the thing. So when you feed that thing data, it knows, what the answer is supposed to be when that answer pops out the other end. That's the whole purpose of training. You give it a series of data and you want an expected answer at the end. So what happens is when you feed this thing data, it goes through that forward pass and it pops out an answer. Well, that answer is probably nowhere near what you want it to be because all the weights are randomized right at the very beginning. So what you do is you compute an error function. You think of it, if you think of a vector is basically an arrow pointing in a direction. Now, in our case, it has 16,000 components, but it's essentially an arrow pointing in a direction. Your answer is going to be another arrow pointing in a different direction. So what you want to do is compute the difference of the answer versus the difference of what you wanted it to be. and then you use that information to back propagate through the model. That's your backwards pass. You propagate, you use that error information to go and update all the weights in the model so that the next time you feed it that prompt or that token, it will give you, you may not give you the right answer, but it will give you a much, much closer answer to what you wanted. Some people call that an error function. Some people call it, in linear algebra, I think they call it a cost function. I don't care what they call it, but essentially you're computing the difference between what you got out of the model versus what you want it to produce. And that's actually a fairly straightforward linear operation, a linear algebra operation. So you go through this thing just a gazillion times. And sometimes, your model, you'll feed it a set of data and the model won't converge. It may come closer to what you want, but it doesn't give you. So you have to go feed the data through again. You call it an epoch. You feed the entire data set through it a second time. But the difference is the model is now not starting in a randomized state. The model is starting in a state that it got when you finished feeding the data through the first time. So the model is closer to what you want, so you feed it through a second time. And you may have to feed it through 3, 4, 5, I don't know. You may have to feed it through multiple times until the model starts producing answers that you want it to produce. Like the guy said earlier in the discussion, you can make an AI model say anything you want it to, depending on what data you feed it. So I put together this sort of little animation to sort of show what happens when you're doing this. And in this case, I used 2 GPUs. You essentially, in this case, you're loading the data from your back-end storage up through the CPU that's controlling the GPUs, and it places a copy of the model in each GPU. Now this assumes that your model can fit within the GPU memory. Then you sit and you stage your first set of training data into the CPU memory. Oops, come on, go back. Okay, now you move the training data from CPU memory into GPU memory. Now, while the GPUs are sitting there crunching on that data, you will pull the next set of data out of your back-end storage, pre-position it in CPU memory, and then wait for the GPUs to complete. So once the GPUs complete, they create a set of gradients or differences. They then exchange these gradients, and during this process, they calculate the error between what they produced and what you actually want, and then they use that to crunch again, and then essentially that's your backward pass. The model gets updated with all the new weights and variances, and then you load your next set of data out of CPU, or you checkpoint it. Sorry, I missed that one. You checkpoint the model, and then you load your next batch of data. And you sit there and ping pong back and forth until the whole thing's completed. So hopefully that makes some sense. So what do we need to do to scale to larger model size? That was a very simple example that shows you have a model that fits entirely within the GPU memory, and you actually have enough GPU memory left over from the model to put your data in and do all these calculations. The problem is if your model gets so big and it takes up almost all your GPU memory, then the amount of memory left over for the data that you're actually crunching on becomes so small, and the batch size of your data becomes so small, it becomes super inefficient because you're spending all that time moving these very little chunks. So the question comes about is like, how do we scale this to bigger and bigger models? So one of the things that you can do is you can either increase the amount of HBM on your GPU. AMD and NVIDIA are both rapidly trying to do that. You do run into some limitations there about how much memory you can effectively pack onto a SoC. It also means that your GPUs become hellishly expensive because you're packing tons and tons of this HBM on there. But another approach is to link the GPUs together so that they form a single memory coherent domain. So that's another approach. And what has been going on is within OCP has, wow, that's different colors. Sorry, this was not my choice of colors, but we'll go with it. Within the OCP group, they have created a standard for what they call a UBB, a Universal Baseboard Module. And essentially that UBB has 8 GPUs sitting on it, all interconnected with a memory coherent mesh. So in this case, I'm using AMD as an example just because I happen to work for them, and they get really mad if I put somebody else's GPUs up on the screen. But this is an example of 8 MI300s put together. They use essentially an infinity fabric, which is our version of XGMI, to create a single memory coherent domain of all 8 GPUs, and then they have a pair of CPUs over there to basically control the traffic coming into the GPUs. So this is, if you go look, this is a picture of what that beast looks like. I can tell you it weighs about 90 pounds. I could not pick it up. It has these incredibly large heat sinks on each GPU. So if I go back to, let's see, yeah, to this picture, this was like a really cool idea, but it immediately, everybody says, okay, where do we go from here? Models are getting so big that we can't fit them into the memory space of 8 GPUs. So where do we go from here? One of the things I want you to notice, when you look at this picture and then look at the physical embodiment of it, essentially we're having to pack these things really, really close together because the XGMI or the Infinity Fabric interface is essentially based on PCIe. You have to pack these things close together because you have an SI problem. You can only drive that interface so fast before the SI channel, the signal integrity degrades to the point where you can't spread them out anymore. So that's one of the reasons these things are packed so close together, is to get all of that information at a very, very high bandwidth interconnect. You have to have them close together. So that limits the number of GPUs we could pack together, and also the number of pins each interface consumes to pack it all together. You run out of space on the GPU for interconnect. So each GPU is interconnected through a by 16 PCIe port, PCIe Gen 5 port to every other. It scales out to about 1.5 terabytes of HBM3. There's 192 gig of HBM3 on each GPU. And OAM is just a GPU. So it gives you about 5.3 terabytes per second max memory bandwidth. It also chews up about 6 kilowatts of power, which means air cooling this thing, we're right at the limit. If we go any higher, we've got to figure out how to liquid cool these things because we just can't. We either have to figure out how to liquid cool them or we have to figure out how to spread them apart so that you can get more air through the system. So this is sort of what is being shipped in mass today, at least from AMD's point of view. So it's these OEM modules. They're eight to a module. They're put into a essentially a GPU server, and then those GPU servers come from a whole litany of OEMs. So I threw some of these up on the screen to basically give you an idea of who's shipping this. We've got Dell, Gigabyte, HPE, Lenovo, Supermicro. They all have a pretty close to the same architecture where it's an OAM with 2 CPUs on it. So the question is, how do we? Curtis would be a better one to answer. I don't know. I think it fits into a 19-inch rack.
There's 19-inch rack standards. You've got
Yeah.
measures on them right there on your slide.
Yeah. So yeah, I'm pretty sure they fit into a 19-inch rack. Some of them are 5U, some of them are 8U, some of them 6U. So yeah, I don't think they're 21-inch rack. So the question is, how do we scale to bigger and bigger deployments? And so the next thing is, here is sort of the next potential architecture that everybody's looking at. And again, I apologize for the colors that the projector likes to scramble them. So essentially what we're looking at in the industry is sort of breaking the thing up into 3 distinct interconnects or networks. So what we want to have is we want to be able to scale this to hundreds of GPUs, maybe even thousands, who knows. But to do that, you really want a network that allows you to create a single memory domain of all the GPUs connected to it. And that's what is known as that scale-up network that sits right in the middle. The properties of that network is it's a memory network. It's a memory coherent network. So the GPUs see the memory of every other GPU on that network. Then there's what we call a scale-out network. So even though you have this big coherent memory domain, there are going to be cases where you can't fit everything within one pod. Now, all of the GPUs connected to that scale-up switch, they're calling a pod. I don't know who came up with that name, but hey, I'm guessing it's somebody from the Pacific Northwest because we have orcas. So anything that is, any GPU that is in a memory coherent domain and can see the memory of any other GPU are within a pod. So if you have to split your job between pods, you need a high performance network that allows you to move data very quickly around. It doesn't have to be memory coherent, but it needs to be a high-speed network. So that's the scale-out network. That allows the GPUs in one pod to talk to GPUs in another pod. And then there's the standard front-side Ethernet, which is the network that connects all of your CPUs that are controlling these GPUs together. And that's generally the network that all of your training data flows into the system, comes through this front-side network. The scale-out and the scale-up are all networks used to sort of facilitate all of the data that gets thrown around within these neural networks. So, yes?
One of the definitions I'm hearing in a lot of scale-up is also what you do in the and so that kind of
Yeah, but there are also, people are talking about multiple rack pods. Oh. The question was the scale-up, one interpretation of the scale-up network was the network that was in the rack that allows the GPUs together. And right now that's pretty much true, but there are also, if you start thinking into the future, a rack can only hold so many GPUs, and there are people that are talking about thousands of GPUs within a pod. So that would span multiple racks. So the scale up is really the network that ties the GPUs together in a memory coherent manner. So now there are a lot of things. Yes, Jürgen?
Yeah, I just wanted to add, I think in the previous model when we talked about UEC, the scale-up network was essentially the HPC.
Yes. The scale-up network in that previous mesh of GPUs that I showed you was the Infinity fabric, was the PCI fabric that tied those together. That was the scale-up network in that particular picture. Now, there's a lot of things going on in the industry. Several new consortiums have been formed to go tackle these problems. The scale-up switch is actually what they're calling Ultra Accelerator Link, UALink, is an industry consortium that's looking at that. The scale-out is Ultra Ethernet. They're looking at that. And actually, if you think about the scale-out has a lot of properties of big HPC systems. So a lot of the work that's being done in Ultra Ethernet also applies to large HPC systems. There are other proposals that are being thrown out for these. I think Broadcom has a proposal for using a variant of Ultra Ethernet to do scale up also. So there's a lot of work going on in the industry to tackle this. But really what you want in this scale up network is the ability to hook more than 8 GPUs together and the ability to go more than like a foot of edge. So you want to be able to span a rack. So that means this interconnect's got to go 3, 4, 5, 6 meters to make it really viable. So that's essentially the vision that is being worked on in the industry to scale these things up. Because to make the training and inferencing, really efficient, you really want that model to reside in a single memory domain. Because once you split it between domains, there's just a god-awful amount of small I/O traffic that has to go between those pods, and it's not very efficient. So you really, really want to keep this in a single memory domain. So that is sort of how the data flows around through these things. Going back to the sort of the beginning a little bit of how you feed this beast. Essentially, I work in the corporate strategy group of AMD, and our GPU and Instinct series, the AI group is growing wildly because we just have an incredible amount of demand for these GPUs. So they are severely resource constrained. And they actually called my boss and said, hey, can Bill come down and take a look at, helping us put together storage implementations for various deployments. And they want you to look at mid-range GPU deployments. So I said, cool, yeah, I'd be more than willing to do that. What do you mean by a mid-range GPU deployment? And they said, well, anything between 5,000 and 100,000 GPUs. And I'm like, mid-range? Oh, yeah. I don't want to see large. So I've been off looking at various customer deployments on how they provision storage to feed these massive clusters of GPUs. And it's really interesting because I heard earlier in the series of discussions, somebody said, oh yeah, there are only going to be like 5 companies doing training and everybody else is doing inferencing. That is not true. There are so many different specialized models being developed out there and being trained that training's going to be done by everybody. I mean, a lot of people don't want to have their proprietary corporate data, being used to train these LLMs. So, they've come up with all these different ways of getting around that. RAG is a good one. But if you think about it, RAG is pretty inefficient because you're having to feed all your corporate data into this model each time you give it a query. So it's like, ugh. So there are a lot of people that are off designing, developing these, I won't call them large language models, but intermediate models to do very specific tasks. So model training is something that's going to be very, very pervasive here very soon. In fact, I would argue it's here now because we're seeing just lots and lots of these neo-scale deployments being built out there. So what I want to do is sort of give you a couple of examples of what we're seeing in actual customer deployments. So here is an example. This is a 9,000 GPU storage cluster that we were involved in putting together. They use 3 tiers of storage. They have the local storage within the GPU cluster itself, so they have a series of SSDs. They have a tier 1 scratch storage area that they use to stage all their training data in, and then they have a tier 2 ingress storage deployment. So, if you look at it, the ingress is about 6.1 petabytes. The scratch storage is about 10.2 petabytes. But they have 35.4 petabytes of local storage. So I went to these guys and we were having all these architectural discussions and I'm like, what are you using these locally attached SSDs for? Because, I know NVIDIA has GPU Direct SSD, but AMD doesn't yet. We're working on it, but we don't. So I was like trying to figure out what are they doing with this? I'm like, oh, you're using it for checkpointing. They're like, no, we don't checkpoint to them. We don't checkpoint to our local SSDs because if a GPU goes down and takes out that node, it takes out that SSD also. So we can't have the checkpoint residing on the locally attached SSD. We need it back in that tier 1 scratch area. So they basically told me that they have 35 petabytes of SSD storage that they don't use, but they think it's going to be important in the future. So they put it in. Oh, 5 minutes. So that was a real enlightenment to me. The other thing they do is if you go back and look at that architecture of the 8 GPUs and the 2 CPUs, what they do is they balance the memory in the CPUs with the GPUs. In fact, they have a little more, like we'll have 1.5 terabytes of HBM in that 8 GPU cluster. They'll put 2 terabytes of DRAM in the CPU, and they checkpoint to the DRAM because it's quick. It's very fast. They checkpoint to the DRAM, and then they slow drain it off to the tier 1 storage. The various tiers, there are lots of companies out there. There's Weka, VAST, Pure, DDN, Hammerspace. There's all these guys. So I was thinking, maybe one of those companies would sort of start to dominate, but not true. Here's a second one. This is a 13,000 GPU cluster. Here they have VAST and Lightbits, and they're actually, I thought, well, maybe one of these companies is good at tier 1 and another company's better at, the tier 2 type stuff. But no, these companies are all over the place. And the other thing that surprised me is I haven't seen a single customer deployment that has one storage vendor. They always have 2 or 3, and they're in different orders. One will have Weka as a tier 0, and the next one will have Weka as a tier 2. It's all over the place. So this is the wild, wild west right now. Everybody's like, there are massive opportunities to sort of make this more efficient. So my conclusions, we're just at the beginning of this thing, man. Everything is getting bigger, everything's getting faster. LLMs are, the talk of the town right now, but there are things like LBMs, large behavioral models, which are used to control robots. Those are starting to come out. These AI systems are evolving very, very quickly to the point where it's not good enough to be a silicon vendor anymore. You have to be a system vendor because all of this stuff fits together and everything affects everything else. So, there are multiple standards efforts going on. UALink, UEC, Open Compute, SNIA's got storage.ai. I mean, there's all this stuff. So essentially, my call to action is get involved. Get involved in these standards efforts. Start understanding that. So thank you. I think we have 1 minute. Sorry, I kind of rambled longer than I thought I would. Any questions? Let me ask this. Did it make sense? Thank you.
Question about the server.
Yes.
31 inches deep, 300 pounds loaded.
Oh, okay. He said the size of the server is 31 inches deep and weighs 300 pounds loaded. Yes, it's no longer a 2-man lift anymore. You need a forklift. So gives a whole new meaning to forklift upgrade. So thank you.